In today's lesson, I want to talk about minerals, specifically to remind us that we are talking about environmental geology. Specifically, this is the interaction between humans and the environment around them, and minerals are one thing that we find in Earth's surface, and of course at depth as well. But we use a lot of mineral resources. You use them every day, whether you realize it or not, in your cell phone and your wristwatch or your alarm clock or whatever else. But you may have learned in 1101 that there's ways that we can identify minerals. But for this class, I want to teach you a little bit about the types of minerals that are out there, the classes of minerals, and how we define them. And then also in lab, we'll spend some time talking about those minerals that are extremely important because of the resources that they provide us. So first of all, let's kind of talk about why it's important to study minerals. Why did you do it in 1101 or 1102? And of course, why are we going to do it again here in a course about environmental geology? So you can probably think of a couple of reasons why it would be important to study minerals. So here's a couple of them that I came up with. They are what make up the materials that we see at the Earth's surface. So if we're talking about what humans are interacting with at the Earth's surface, those Earth materials are going to be made up of minerals. Think of it this way. Minerals are the ingredients or are the building blocks of the rocks and the materials that we see at Earth's surface. So the properties of the minerals are going to then dictate the properties of those Earth materials as well. They also, of course, the material that is made up of certain minerals is going to have those same characteristics as the mineral. So for example, if you have a mineral that is particularly soft, something like gypsum, where you can scratch gypsum, the mineral, with your fingernail, a material that you make out of that mineral is going to have a very similar characteristic, which is why we use gypsum in drywall or what people call wallboard. So you can kind of just score it with a razor and then snap it with your hands. So the materials behave in certain ways depending on the mineral composition. Industrial minerals, and we're going to talk about those in lab specifically, they will be the raw materials for manufacturing. So we're going to be looking at both metallic and non-metal bearing minerals and the importance of all of those for certain industries. For example, the glass industry, computer industries, electronics, and then of course too things like alternative energy industries. So we'll talk about some of those industrial minerals that are going to be those raw materials for manufacturing. We'll also talk too about ore minerals. So minerals are usually compilations of certain types of ions, right? So positive or negatively charged atoms are called ions. And some of those cations are going to be metals, right? So things like iron, nickel, titanium, lead, those can be really important metal ores, but they may be mixed with something else like oxygen or sulfur. But we can still get at those metals within those ore minerals, and then we just have to separate the metal that we want from the actual ore rock that it's in. So we'll talk about that a little bit later on in today's lesson also. Oops, I don't know why I did that in individual lines, but that's okay. So those are our ore minerals. And of course, too, you know, there is a huge economic industry associated with gem minerals. And all the different flavors therein, from natural minerals, but also to synthetic minerals that are actually a really big market right now. So, okay, we're talking about why we study minerals. Let's think now, what is an actual mineral? This probably comes to mind when you think about what is a mineral, right? I know we've all seen quartz crystals like this, but what is the actual definition of a mineral? Why is this crystal right here, which is a quartz crystal, which is made up of silicon and oxygen, okay, that's SiO2, how come this version of SiO2 is a mineral, but glass, which has the same exact composition, is not a mineral? So what is the definition of an actual mineral? Here's the characteristics of what we would consider a mineral. So the thing that we have to have here is that the mineral is a homogeneous material. What does that mean by homogeneous? It means that the actual solid, and so we're talking about like, you know, the crystal or something here, cannot be broken down into anything simpler. I don't mean that it can't be broken down into its elemental constituents, right? Like we can break this down into silicon and oxygen, but what I mean is that the actual crystal itself is all made up of the same stuff, right? Just silicon and oxygen. You cannot break it down into something simpler. So it has to be homogeneous. It has to be silicon and oxygen, right? It has to be the same mineral composition throughout. Now remember, I'm using silicon and oxygen for this example because this mineral here is quartz. Not all minerals have to have silicon and oxygen, but they do have to be all homogeneous. They have to have the same chemical composition throughout. They also have to be naturally occurring, right? So minerals that we would find maybe produced in a laboratory, we call those synthetic minerals, but generally speaking, a mineral is naturally occurring. So we can find it somewhere forming naturally in the environment. It also needs to be solid, so it literally can't flow or have any sort of fluid abilities. That's one of the reasons why glass actually is not a mineral, because it does flow over time. A mineral has to also be inorganic, right? So we're not going to talk about things that are organically produced. So for example, carbon in its inorganic form can create diamonds, but carbon can also be in the organic form. Diamonds are minerals, but organic carbon is not. A mineral also has to have a definable chemical composition, and I've written over here within limits. What I mean by having a definable chemical composition means that we can write that a mineral has certain elemental constituents. So for example, this is the mineral calcite. This is calcium and carbonate. Now, what I mean by within limits is that some minerals can substitute, and you can have calcium or magnesium. Oops, carbonate. I don't know why I wrote that. There we go. But this is the same mineral. This is calcite. We've just substituted a little bit of magnesium within it, hence the idea that, you know, you can have some substitution of certain ions within limits, but that this is still, in the end, still the calcite mineral that we started with here, because we're just adding a little bit of substitution of something else. The actual atomic arrangement of the calcium and the carbonate ions still makes that calcite. Last but not least, too, our inorganic, homogeneous, naturally occurring solid has to have a crystalline structure. So I'm sure you've seen these before, these little ball and stick models, right, where you have atoms as the little balls, and then the sticks are showing the atomic bonds between those atoms. And so we have a crystalline structure here that usually has very few vacancies, and so the crystal actually then grows into the shape of what that mineral looks like. So for example, here is a well-formed crystal of quartz. Shows that beautiful six-sided prism. So how do minerals form at the atomic level? I just want to remind ourselves of some basic chemistry before we go on. Remember that all atoms are going to have a nucleus, right? So there's our nucleus of our atom, and in the nucleus you've got your protons. And remember that protons here have a positive charge, right? And then also in the nucleus you have neutrons, right? Neutrons don't have a charge. And then around all of that, you've got your electrons, and the electrons, of course, have a negative charge, right? The other thing to remember, too, is what things actually have mass versus what things have charge. Protons and electrons have charge, but protons and neutrons have mass. This comes into our discussion then, the what has charge versus what has mass, when we talk about the atomic number versus the atomic weight or the atomic mass. So you could write that too as atomic mass if you wanted. Remember that the number of protons in an element yields the atomic number. So carbon will always have an atomic number of 6. Oxygen will always have an atomic number of 8. It's the number of protons that defines the actual element, right? Carbon always has 6 protons. Oxygen always has 8 protons. The atomic mass, or the atomic weight, though, takes into account the number of protons plus the number of neutrons, because we have both protons and neutrons adding mass. So if an oxygen atom has 8 protons and 8 neutrons, it has an atomic weight, or an atomic mass, of 16. So just remember, who has mass? Protons and neutrons. But who has charge? Right? That's protons and electrons. Minerals are going to form at the atomic level because those atoms are going to come together by means of chemical bonding. And I'm sure you remember from your intro chemistry course the different types of chemical bonding, and we'll go over those briefly in a second. But the reason why atoms come together and bond is because they desire stability. Remember that you have electrons in the outer shells of your atoms. Some atoms have a couple of extra, some are missing just a couple. And so neighboring atoms can either share or transfer electrons in order to become more and more stable. So if we remember this from intro chemistry, we should hopefully then too remember that we can look at the periodic table and figure out which elements have a couple of extra electrons that they would rather get rid of versus missing just a couple of electrons that they would rather gain. Here's the periodic chart, and so hopefully you remember this from intro chemistry. And if we remind ourselves how to orient our view of the periodic table, those elements that are on the left side of the periodic chart, so we're looking over in this region over here, right? Those guys on the left side of the periodic chart have a couple of extra electrons, right? The first column has maybe 1 extra electron. The second column here in yellow maybe has 2 extra electrons. And so these elements here tend to give up an electron or 2. And if they give up, so for example, here's hydrogen, right? Hydrogen has 1 proton and 1 electron. If hydrogen gives up its electron, right? If we take this electron and we give it away, does it make sense that hydrogen now has a positive charge, right? Because it only has 1 proton, and protons have positive charge. What that means is that elements that are here in the column that is orange and in the column that is yellow, these elements tend to give up 1 electron if they're in the first column and 2 electrons if they're in the second column. And when they do this, they become positively charged, and positively charged ions we call cations. A good way to remember this, guys, is if you think about the T in cation, right? The T there, the T is a plus. So in a cation, it's the positively charged ions. And how do you get positively charged? You do it by giving away an electron. Now let's come over here to the other side of the periodic chart. I'm going to look at the green guys over here. So we're looking in this region. These elements over here are missing 1 or 2 electrons in their outermost shells. So in order to gain stability, they would prefer to gain an electron or 2. And by gaining electrons, that means you are gaining, right? I always use my E- as my shorthand for electrons. If you gain a negative charge, that means that you become an anion. So anions are negatively charged atoms. And so if you're in this column here with fluorine, chlorine, bromium, and iodine, you tend to gain 1 extra electron and you have a -1 oxidation number. If you're in the column here with oxygen, sulfur, and selenium, you would tend to accept an extra 2 electrons, and so you'd have a -2 oxidation number. All of these elements here are anions because they have a negative charge once they accept extra electrons. So if this makes sense to you, you should be able to fill out this fill in the blank question here. Let's see if we can remember. Elements on the left side of the periodic table tend to gain or lose electrons to become cations or anions. So if you remember that on the left side of the periodic chart, right, the left side, these are going to become cations, right? And in order to become a cation, you tend to lose electrons. You give up electrons to become positively charged. And if that's correct, then the next part should be elements on the right side of the periodic table tend to gain electrons and become negatively charged, which is then anions. So remember, it's the ions that have charge, and we can remember how we can gain or lose electrons based on which side of the periodic chart we're on. So remember, you can kind of test yourself with these questions here. And of course, too, every time I give you questions like this on a PowerPoint, I'll always give you the answers. Okay? So let's go over the types of chemical bonding that you probably learned in intro chemistry. The first one we're going to talk about is one of the strongest ones. So these are covalent bonds. These are where you have the sharing of outer electrons. And so I'll put here too, sharing of electrons, it's mainly the outer shell electrons here. A good example of this is the covalent bonding of carbon atoms in diamond. And of course, you know that diamond is an extremely strong mineral, and part of the reason for that is because all of the carbon atoms within a diamond are covalently bonded to neighboring carbon atoms. So covalent bonds are very strong types of bonds. We also have ionic bonds. For example, if you have a sodium atom and it gives up an electron, it becomes positively charged. When you have a chlorine atom, it accepts an electron to become negatively charged. You can now get an attraction between oppositely charged ions, the sodium cation and the chlorine anion, and that can create something called an ionic bond. Now, ionic bonds are relatively weak, and we know that because this mineral that I've listed right here, Na and Cl, this is salt. If you put salt on your tongue, you can dissolve it. The dissolving of salt on your tongue is literally the water molecules on your tongue breaking the weak ionic bond between the sodium and chlorine ions. So, covalent bonds are very strong, and ionic bonds are relatively weak. Lastly, the ones that we're going to talk about, and I know that there's lots of other types, right, like hydrogen bonds and polarity bonds and whatever else, but the last one I want to talk about here are metallic bonds. Metallic bonds are where you're sharing electrons again, but you're sharing the inner electrons. So literally when metal atoms bond metallically, so something like, iron or gold or silver or something like that, they're not only sharing the outer electron shells, but they're also sharing electrons from the inner shells. This might make sense as to why metal is a good conductor of electricity. Electricity essentially is just a flow of electrons. And so if you have two neighboring iron atoms, and they're literally sharing electrons from both the outer and inner shells, you're setting up a flow of electrons, and that is an electrical current. So metallic bonds, usually with metal atoms, you're not only sharing the outer electrons, but you're also sharing the inner electrons. Very strong bond for metals. Couple ways to just remember this, right? Here's your ionic bonds up at the top, right? This is where you're literally oppositely attracted, bonding there. They are just different types. One would be positive, one would be negative, and opposites attract. Here's your covalent bonds showing the sharing in the middle there. And then the metallic bonds at the bottom here showing essentially that you're sharing not only the inner but also the outer electrons between the two. So some minerals actually have the same chemical composition. So they may have the same chemical formula, so the same chemical makeup, but they have different types of bonding. And so when we have those minerals, we call those polymorphs. So poly means many, and morph means form, right? So there's many forms of the same type of chemical composition. Here's a good example. This is graphite and this is diamond. Both of them are just made up of the element carbon. So both of them have nothing in them but carbon atoms. However, graphite is very weak In fact, you can put it in your pencil and then you can actually break the bonds between the carbon atoms just by wiping your pencil across the paper. But diamond is very strong and it's still all just carbon. But the reason why diamond is much stronger than graphite is because diamond has covalent bonding. All of the different carbon atoms are held together by strong covalent bonds, whereas graphite has very weak bonds between the sheets of carbon atoms, and that's what you can break when you rub your pencil across a piece of paper. So polymorphs can have the same chemical composition, but they are very different minerals with very different properties because they have very different types of internal bonding. So how do we get minerals to form? There's three main ways that we can get minerals to form in a natural situation. And I'm going to give you examples of each of these. The first one here is solidification of a melt. So you have something that is in liquid form, and then you change the temperature of that liquid, and you actually can create a solid from that fluid. You actually can then also have precipitation from a liquid solution here. Now this is slightly different. This is not changing temperature. This is essentially driving off the water from a solution and leaving behind a solid, as if you had, like a beaker full of water, and then you started to grow little salt crystals in the bottom of it. Lastly, we'll talk about something called solid state diffusion, right? This is where you can literally have a little bit of temperature change, or a little bit of heat, and you can have fluids moving through a material, and that can move ions around slightly. So we're not talking very far, just local movement of ions, and you can create new minerals that way. But let's look at this idea of making minerals by each of these mechanisms. Solidification from a melt, a good way to think about this is ice. Here's a lake, and this is at the surface of the lake, right? The temperature has gotten a lot colder, and so the water has actually started to cool down. It has crystallized, and it has crystallized into the form of ice. So the water is the melt, and the mineral that is forming from that is ice. It is a crystalline, inorganic, homogeneous solid. So beautiful example there of a ice as a mineral forming from the cooling down of a liquid water melt. If anybody's ever been caving, here's a good example of beautiful stalagmites and stalactites from a cave. And this is an example of precipitation from a solution. So the minerals that are in this cave structure up here, the mineral that most of this is made out of is calcite, CaCO3. Now that's dissolved in the water as calcium and carbonate ions. But as the water either evaporates or as it becomes supersaturated with those ions, the ions can move around in the solution. They can find each other and start to precipitate from that solution as a solid. So this is all calcium carbonate solid in this cave right here that precipitated out of the water that was flowing through this cave. We can also destroy this, of course. We can make caves by destroying the calcium carbonate when we actually dissolve it by putting water back into the system. But that's that's the opposite of precipitation from a solution. Okay, bear with me for a minute because I want to talk about a game I had when I was a kid. I'm not sure if you ever played this game, but when you were younger, did you have a game that looked like this? It had maybe spaces for 9 tiles, but there were only 8 tiles. There was 1 empty space in the tile game. And what you could do is that part of the game was to shift the tiles around, right? Move this one over here, then move this one down and whatever else. And you could actually then make a puzzle out of it. Do you remember that game when you were younger? That's kind of the principle behind recrystallization. You're not really adding a lot or you're not really taking a lot away, right? You still have the same 8 tiles in the game, but you're just kind of shifting them around a little bit to make the game look a little bit different. So with a little bit of heat and a little bit of pressure, we're not melting anything here, but we're just adding a little bit of heat and a little bit of pressure. What can happen is that atoms inside a rock can start to move around a little bit. They can then recombine to make recrystallized minerals. This happens a lot in rocks that have been put under heat and under pressure. And if you remember that, these are called metamorphic rocks. So we see a lot of this around Boone. Here's a good example. This is a rock type called a gneiss. This was subjected to high heat and high pressure during mountain building. And so all the big white blobs that you see in this rock here, these are a mineral called feldspars that have been recrystallized during the metamorphic process. All of the constituents of those minerals were in that rock to begin with, but we just kind of played this shuffle game during heating and squeezing to form those new feldspar minerals during metamorphism. So now that we know how we can make minerals, let's talk about the actual constituents of those minerals. So where do we get the composition of the minerals? If we look at the elemental composition of the whole Earth, so if you look at the one on the left here, you can see that the 3 or 4 most abundant elements in the entire Earth, so I'm not just talking about the Earth's surface, I'm talking about the entire planet. The 4 most abundant elements are iron, and so remember iron is Fe, oxygen, silicon, Si, and magnesium, Mg. So I've got those over here. Greater than 90% of the Earth is made up of iron, magnesium, silicon, and oxygen. If we then look at just the Earth's crust, what you'll notice is that there's a couple of elements that are very abundant still in the Earth's crust, namely the silicon and the oxygen. But what actually happens too is that the 3rd most abundant is now going to be aluminum instead of iron or magnesium. This is really important because iron and magnesium are heavier or denser elements than aluminum is. And so aluminum here is a lower density, lighter element, so it makes up the outer part or the surface of the Earth, whereas magnesium and iron are really heavy and they make up the inner parts of the Earth. And you remember now too from your intro geology course, right, 1101, that that's what helps us define that the inner part of the planet, the mantle and the core, are made up of iron and magnesium rich elements, but that the Earth's surface is a lot lighter and made up of aluminum rich materials. Minerals are grouped together by 2 major characteristics, and I can promise you that this will be showing up on a quiz or an exam sometime soon. We can group minerals by 2 main characteristics. The first one is by their chemical composition, and the second one is by their atomic structure. So the chemical composition, what do I mean by that? It's literally what are the elements that make up that mineral. So it means that we can write out a formula, right, for our minerals. For example, Si, that's silicon, and then O2, that's oxygen. That's the mineral that we call quartz. Okay, so the chemical composition is really important, and that's one way that we can separate different minerals. Minerals that have, for example, silicon in them will have certain properties. Minerals that have things like iron will have properties. You can imagine that minerals that have metals in them will be good conductors. And so the mineral properties that are often affected by the chemical composition are things like the specific gravity, literally the density. How heavy does a mineral feel? You can imagine that a mineral that has a lot of lead in it is going to be really heavy, but a mineral that has a lot of a lighter element like aluminum in it will not be quite so dense. The color of minerals is dictated somewhat by their chemical composition. In fact, you know that the mineral quartz comes in a whole variety of different colors, pretty much all colors of the rainbow. And the reason for that is because just by adding a little bit of a new element to the silicon and oxygen and quartz, you can create color. Adding a little bit of iron can make it red. Adding a little bit of cobalt or lithium can make it blue or purple. So the color actually is often dictated by the chemical composition. Last but not least, you might remember that minerals also have what's called a streak, and that the streak can be very different from whatever the mineral's outward color is. The streak is the color of the mineral when it is powdered. And specifically, we powder those minerals by rubbing them and scraping them across a ceramic plate. And so the streak is the color of the mineral when it is powdered. That may seem a little bit strange, but many minerals have an outward color that is extremely different from their powdered color. Quartz can have an outward color of purple, pink, white, black, green, yellow, orange, but even though its outward color can change, its streak color is always white. So streak may not change, and that's a very important diagnostic or unchanging property of the mineral, even though small contamination in the mineral can give its outward color a very different look. So the streak color is dictated by the chemical composition, just like the outward color is. Now, the second way that we can group minerals is by the atomic structure. So literally, we're talking about now the arrangement of atoms in terms of how the atoms come together, not only with the bonds, but also with the type of stacking of the atoms. Are the atoms stacked in like a cubic structure, right? Like this. Are they stacked in a cubic structure, or are they stacked more tightly together, right? Something like this. These will dictate things like the hardness of the mineral, right? That has to do with the bonding. Are we able to break the bonds or not? And a property of minerals that we call cleavage. Cleavage is the ability of a mineral to break along planes of very weak bonds. So you can think of, of what a cleaver is, right? A cleaver is a big flat metal knife. So if you cleave a mineral, right, it will break along flat, repeating surfaces of very weak bonds. There are over 3,500 recognized minerals on Earth. We are not going to learn about all of them. Instead, what I think is more important, we'll look at quite a few of these minerals during our lab, but rather than learning all 3,500 minerals, I think it's much more important that if we realize that minerals are grouped into certain chemical groups. So for example, of the 3,500 recognized minerals on Earth, the most abundant group of minerals are those that are what we call the silicate minerals. Silicate minerals here all have silicon and oxygen in them. So it's very easy to look at a mineral's composition and say, it has silicon, it has oxygen. They are bonded together in what we'll call the silica tetrahedra. I'll show you that in a minute. And therefore, all minerals that have that grouping are called silicate minerals. Silicate minerals, most abundant not only in the earth, but at the Earth's surface. And so lots of minerals that you'll be familiar with, notice that things like quartzes and feldspars are going to be silicate minerals. There's lots of other types of minerals too, but the main groups are going to be things like carbonate minerals. They will all have the CO3 anion. So you can have, for example, calcite, which is calcium carbonate. And that's a good example of a carbonate mineral. You can have oxide minerals, right? Oxide minerals are going to have the oxygen anion. Things like hematite, right? Hematite are iron plus oxygen, so iron oxides. You can have sulfide minerals. They're going to have the sulfur anion. Pyrite is a good example of this, right? That's Fes2, right? So that's iron sulfide right there. You can have groups called halides. Halides are going to have the halide elements in them. Those are the ones that are in the second to last column of the periodic chart, right? Fluorine, chlorine, bromine, and iodine. Salt is a good example of a halide because it is made up of Na and Cl. There's the Cl anion at the end, which makes salt or halite a halide mineral. Now, different from the sulfides is this last one here called sulfates. Instead of sulfide minerals, right, which just have the sulfur anion, sulfates have the sulfur and oxygen anion. So you're going to look for the SO4 anion there. And an example there is gypsum, which is calcium sulfate. Last but not least, you also can have, and we'll talk about this in a little bit, native elements. So literally you're going to just have mineral groups that are made up of just the actual element. So things like gold and silver are good examples of native elements. They are not mixed with any other major ions. They are just the metal atoms. Without going through all the different types of groups of minerals, I just want to focus mainly on the silicates and the carbonate minerals. Mainly the silicates are important because they are the most abundant groups of minerals excuse me, that we see at the Earth's surface. And so we're going to use them for a lot of different industries and manufacturing. All silicate minerals contain silicon. Ooh, you can't see that, can you? Contain silicon and oxygen. The silicon is an Si atom here, and each silicon atom is then going to be bonded to 4 oxygen atoms. So what we're going to make is SiO4, okay? This is going to be what we call the silica, Si, tetra 4-hedra, or a single one is called the silica tetrahedron. So here's your little silicon atom right in the middle, right? And here's your 4 oxygens, 1, 2, 3, 4. And they're arranged in this kind of pyramid shape. That's the tetrahedra part, right? That's the kind of pyramid shape that we're going to use to make all silicate minerals. So you can imagine that silicate minerals are kind of like cupcakes. I love to relate anything and everything to food. So let's imagine that for all silicate minerals, right, the basic ingredient is you have to have SiO4 tetrahedra. Now, you can make all different types of silicate minerals just by adding different ingredients. So for example, potassium feldspar over here is one example of a very popular silicate mineral. We need the SiO4, but if we just add things like a little potassium and a little bit of aluminum, we can make potassium feldspar, which is a type of silicate. Micas are a type of sheet silicate, so we need the SiO4, but we just need to add a little bit of things like aluminum and maybe magnesium, and we can make mica minerals. We also have a group of silicate minerals that we call ferromagnesians. Ferro, right, stands for the Fe in iron, and then you also have the magnesium. So if we have the silica tetrahedron and we just add a little bit of iron or magnesium to our recipe, now we can make ferromagnesian silicates. So think of it this way, right? Silicate minerals have to have the same basic SiO4 ingredient. They have to have the silica tetrahedron. But all we have to do is add a little bit of different ingredients and we can make different flavors of silicates. Here's a great example of a bunch of different silicate minerals. Along the bottom of the slide, you'll see that we're going to go from olivine over here through all these different types of silicate minerals, and over here we have potassium feldspar. All of these minerals are silicate minerals, which means that they all start out with the basic recipe of silica tetrahedron. And so down here, what we're trying to show is that each of these little pyramids right here, right, each of these little pyramids is representing a silica tetrahedron. Olivine is a very simple mineral, right? It's very easy to form. It forms at high temperatures, usually in volcanoes. And it is just essentially isolated silica tetrahedron with magnesium and a little bit of iron. As we then get into more complex types of minerals, things like minerals here that are what we call single chain silicates, we start to now bond the neighboring tetrahedron to each other by having a single bond between neighboring tetrahedron that is covalent. Remember, covalent bonds are very strong. So single chain minerals now have a single chain of silica tetrahedron plus the other ingredients, right? And we make a group of minerals called pyroxenes. You can then have a new, more complex group of minerals called the double chain silicate minerals. Notice now how we're getting a little bit more complex in terms of the way that our tetrahedra are bonding to each other. So there's the way that the tetrahedra bond. We'll add the ingredients to all of that too, and we'll get minerals called amphiboles. If you keep bonding the corners of the tetrahedron to the neighboring tetrahedron with covalent bonds, you're going to get sheet silicates. These are going to be the mica minerals